recording, and let me share my screen. Share a screen and book. Okay. Okay, guys. So last time we finished chapter 2, and today we are going to start the new chapter. The new chapter is the random variables and the probability distributions. Random variables, that means it is nothing but a function. You know that in a function we have a domain and codomain, or you can say a range. Range is always a subset of a codomain, right? So one side we have a range, another side we have a codomain, and function that assigns each and every value from the domain to the codomain. So that's what we mean by the function. So naturally, as I told you, that random variables is a function in terms of statistical language. So that means whatever the domain we decided, we defined in our function terminology, here our domain is nothing but our sample space. So sample space is assigned to some numbers depending on the context of the problem, how the sample space, each and every element of the sample space is assigned by some numbers, maybe 0, 1, 3, something like that, depending, as I told you, on the context of the problem. So that is nothing but the random variable. And we are going to find now the probability distribution based on this random variable. So there are two types of probability distributions. One is discrete probability distribution, and second one is continuous probability distribution, that is called CPD, continuous probability distribution, and discrete probability distribution. So that's what we are going to learn in article 3.1, 3.2, and 3.3. And then after we'll go over a few of the examples. So that is the today's content. So let me start here. You can see here that the testing of a number of electronic components is an example of a statistical experiment. All of us, we know this thing regarding this matter. For example, the sample space giving a detailed description of each possible outcomes when 3 electronic components are tested by this one. Now, 3 electronic components, suppose there are production of components on a line, and if you pick 3 electronic components and these randomly selected 3 electronic components, you need to verify that whether these out of these 3 electronic components, whether all of these 3 electronic components are non-defective. Non-defective because starts with N, so I would like to denote by N, and defective I would like to denote by capital D. So what is my sample space? You can see over here my sample space. Try to look at my cursor. My sample space is N, all 3 are non-defective, or it may possible that first 2 are non-defective and third one is defective, or first one is non-defective, second one is defective, third one is non-defective, or first one is defective and other 2 are non-defective, or first one is now non-defective and other 2 are defectives. So you can always play with this one. And then defective, non-defective, and defective, or defective, defective, and non-defective. All, it may possible that all 3 are non-defectives. So all 3 are defectives. So that means my sample space contains these 8 elements. You can see over here. So how many, we are looking for the defective pieces. So if I want to assign this first part, because this is now my sample space, this sample space, that is my domain in terms of function, and random variable, we are going to assign one function with respect to this domain, this sample space. And our outcome is nothing but to find the number of defective component, electronic component. Number of defective components, here in first case, we don't have any defective components. So this N and N will be assigned the number 0 because no defective components are 0. Then we have one defective component in the second, for the second sample space. That means we assign the number 1 because 1 is defective. Same here for the third component, that is the third category. Again, we have 1 defective. So again, this will go to 1. This next one will again go to 1 because 1 defective. Then after we have 2 defectives, so this number will go to 2. So we have 0, then 1, and now 2. Then again, so this will go to 2. Then again 2 defectives. So this number, this one will be assigned to number 2. And finally, we have 3. So that means our codomain, or I would say range for this sample space in terms of the random variable, this range will be 0 because first one is assigned to 0, no defective, or 1 defective. So 0, then 1, then 2, and 3. So 0, 1, 2, 3, these 4 elements are there in the range of the sample space, range of the sample space. Again, let me share my whiteboard so that will probably give you more idea. So usually, as you know, that very frequent I'm moving to whiteboard so that you guys can come to know. So first of all, let me write the definition for you, and then after I'm going to come back to the same example. A random variable for function that associates. See again, look at over here is just a definition like for function. So a random variable is a function. All of you know about the function because we went over this type of function, domain, codomain, all these terminologies in 9th, 10th grade. So it's a function that associates a real number with each element in the sample space. That means, as I told you, that this is my codomain, or I mean, this is my domain, but in terms of random variable, this is my sample space. So sample space I would like to define by as elements are n, then n, d, then n, d, and then d, n, d. D, n, n, right? D, n, n. Then after n, d, then d, n, d, then d, n, then d, n, d. So 8 elements. As I told you that there is a function, this is some function assigned to some numbers. This is my codomain, or you can say range of a function, and this is my random variable. So my random variable I would like to denote by x. So random variable denoted by capital X. So this X assigned, suppose this one is assigned over here, so number 0. Then this one is assigned over here, that is number 1. Then again one defective, again one defective, so all this will go to the number 1. 2 defectives, so this will go to number 2. This is 2 defectives, again 2 defectives, so this will go to number 2. And 3 defectives, so this will go to number 3, right? So this way we have 1, 2, and 3. So these are the 3 total defective items. Suppose I want to go for a probability of this one, then what will happen that I'm looking for the 2 defectives. So we shall use a capital letter X, as I told you, to denote the regular random variable, and its corresponding letter small x in the case for one of its values, right? So small x for the one of its values. So these are nothing. This is small x and this is capital X. That means it's a x is a function of x, something like this we can say. And there is nothing but some real number. So in the electronic component testing illustration example, whatever I give it to you, we notice that the random variable x assumes in the value 2 for all elements in the subset. Now 2 value that is associated, let me change the color. So probably this 2 value that is associated with these 3 components, because 2 defectives, and 2 defectives are there for these 3. 2 defectives. And suppose I denote this one by this one separately, 2 defectives, that is some space, subspace, sample space, I would say, that is NDD, NDD, then DND, then DDN, then DDN. So my subset is this one of the sample space S. This is a subspace of sample space S. That is, each possible value of X represents an event that there is a subset of a sample space for the given experiment. Then after, I would like to go to another example in which, suppose we have 2 balls are drawn in a succession without replacement. Now, please keep in mind this thing, that without replacement, 2 balls are drawn, right? So 2 balls are drawn without replacement from an urn containing a red balls, I mean say 4 red balls and 3 black balls. So now in my second example, I have, this is the first one, my second example, I have, yes, 4 red balls and 3 black balls. 4 red balls and 3 black balls. The possible outcomes and the values of y of the variable y. So 4 rate balls. So my capital Y, that is my random variable, and small y. So y is the number of rate balls. This y is capital Y is the number of rate balls. Number of rate balls. Right? So possible outcome and the values y of the random variable y, where y is the number of rate balls. So first of all, let me write the sample space. My sample space, that is capital Y, or you can say sample space S. Y is the random variable, and small y, that is my number. Here I said this one, but actually this x is this one. This x is equal to 0, 1, 2, 3. Okay, and small y is the number. So here I want to pick what are the possibilities, because 2 balls are drawn succession. You are going to pick out of these 4 red balls and 3 black balls. So if you pick one that is red randomly, and then you are not replacing back, you are keeping with you, and then after another ball, so 2 balls are drawn in succession without replacement. It could be possible that both are red. So both are red. It could be possible that first one is red and second one is black. It could be possible that first one is black and second one is red. It could be possible that both are black, right? Both are black. And you are looking for your function sample space, that is the 2 balls and both of them are red. If it is red, that means this one is assigned to 2, this one is assigned to 1, this one is assigned to 1, and there is no red. That means that is equal to 0. So that is what we mean by my function is nothing but the number of red balls. Y is the number of red balls. So this is my, you can say, domain or the sample space. This is my small y, and the function here, capital Y, that is number of red balls. So number of red balls. And you can see over here 2 red balls, so number 2. So that means this function, this random variable, assigns the values 0, 1, and 2. 0, 1, and 2. Now, I would like to go for, let me just save this part. Okay. And let me go through the third example. So my third example, that is really good example, and we will be continuing with this example, or we are going to refer this example multiple times in this chapter. So first of all, let me again stop sharing this one and let me share my book, so that, and then after I will explain to you. So first of all, let me just try to go for my third example. So third example is something over here. Look at here, guys. A stockroom clerk returns 3 safety helmets at random to 3 steel mill employees who had previously checked them. Smith, Jones, and Brown. Now, Smith means I would like to denote by S, John I would like to denote by J, and Brown I would like to denote by B. So S, J, and B, like this. This is the order. This is the order we are going to follow if Smith, John, and Brown is a set in that orders. Look at here. So this is my perfect order. Receive one of the 3 hats, or you can say helmets. List the sample points for the possible orders of returning the helmets. Right? So how many possible orders are there to return the helmets, and find the value M, of the random variable. Value M is my numbers, and M is nothing but there's capital M, that is my random variable. Capital M represents the numbers of correct matches. Number of correct matches. Now, guys, language used here in the book that is not that that obvious. So I would say that please try to pay attention over here. Just make sense that Smith, Jones, and Brown, if that is in that sequence, Smith, Jones, and Brown, that means there is a correct order, and correct order, that means we have 3 because they are returning in that form. So that is 3, right? That is 3. If something is not in this form, that means we need to figure it out, that how we get this number 1 and 0 like this. There is no 2. So it's not like this always you're going to get 0, 1, 2, 3 like this. No. As I told you, depending on the context of the problem, sometimes our number, see, doesn't go in a sequence. Some of the numbers are broken. We can break the sequence too, right? So let me just go back again and try to solve this problem. And then after, again, we will go back to the another, again, we will be referring the book. So my whiteboard, let me clean this part. So clear all drawings. And now, as I told you that Smith, and then after John and Brown. So Smith, John and Brown, this is the correct order. First of all, let me write my sample space. So my sample space contains number of elements. So SBJ or sorry, SJB, then SBJ, then SBJ, then I can write BSJ, and then BSJ, then after I can write JSB, then after I can write JSB, then JBS, and finally I can write BSJ. So these are the possible arrangements of these three numbers or three people, these three persons, Smith, John, and Brown. So Smith, John, and Brown, or Smith, Brown, and John, or Brown, Smith, and John, or John, Smith, and Brown, or John, Brown, and Smith, and Brown, Smith, and John, like this. This is the order. If this is the order, that is assigned the number 3. That is assigned the number 3, and that is my small m, and my capital M, that is nothing but the number in this correct order. Whatever is given, capital M is the random variable M that represents the number of the correct matches. So random variable represents the number of correct matches, and correct match is SBJ. Now for second number, you can see here S and S are there, that is, they are in the same order, but these are not in the same order. So only one is matching. So I would like to write 1. For my here B with S, then S with J, and J with B. So none of them is matching. So I would say that third one will go to 0. Third one, if I'm not wrong, the third one will go to 0. Let me just double check. SJB, then SBJ. Let me verify SBJ, if I write all my sample space in a right order or not. Let me just make sure, guys. So SJB, then SBJ, then BJ. Actually, it should be BJS, right? I did one mistake over here, BJS, but I think that is fine. BJ, okay, let me use this one. Little mistake, guys, I'm sorry about this. So eraser, and that eraser will be here. Okay. Okay, so let me just verify. Smith, John, and Brown, then SBJ, then BJS. So let me write here B, J, and S. That makes more sense. And then after JSB, then JBS and BSJ. Because this one and this one was matching, actually. That was same previously, but now this makes more sense. Okay, so now S with S, let me change the color. Probably that will give you more idea. So S with S, and that's why we have one matching, but these two are not matching because B is not with J, and so that is equal to just 1. Then after B, you can see where B with J not matching, but this one is matching. Look at here, J and J. So here, this one will now go to 1. This one will go to 1. Okay, and then after, and this one is not matching. Look at here, this one is not matching. Now J with S, so that is not matching. S with J, that is not matching, but B with B, this one is matching. So this is the right match. So I would say that this goes to 1 also. Now J goes to S, not matching. B goes to J, not matching. S goes to B, not matching. So this will go to 0. Same way, B goes to S, not matching. S goes to J, not matching. And J goes to B, not matching. So this will again go to 0, right? So my M is nothing but in this case 0, 1, and 3. 0, 1, and 3. So that's how you can write the numbers. Now, so far you can see over here that we have some numbers on in my set small m, that 0, 1, 2, 0, 1, 3 or 0, 1, 2, 3 or something like that. Some numbers are there, but always it is not possible to assign some number. In that case, suppose you have infinitely many terms are there over here in small m in this set. At that place, that time it is not possible to write the number of of the numbers. In that case, we are going to assign some value. So we can say something like this, that other example, I can say that in each of these two preceding examples, the sample space contains the finite number of elements. Sample space contains the finite number of elements. I mean to say this one, that 0, 1, 3, previously 0, 1, 2, or 0, 1, 2, 3, like this, finite number of elements. On the other hand, when the die is thrown until 5 occurs, if you throw a die until 5 occurs, we obtain a sample space with an unending sequence of elements, right? Until 5 occurs. So it may be possible if you throw a die and until 5 occurs, it may be possible that first time 5 occurs, or it may be possible first time non-5, second time 5 occurs. It may be possible first time non-5, second time non-5, 5 is not there, but third time 5 occurs. It may be possible if you roll a die, that means first 3 times 5 is not occurring and fourth time 5 occurs. Or it may be possible that every time you throw the die and every time you're going to get non-5, 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 non-5 for number of times, for 50 times, 20 times, 100 times, 500 times, it could be possible. So there is infinity many elements in the sample space. So so whenever we have this type of situation, at that time we have to assign some number, some random variable x, which assigns this sample space, right, guys? So but even in this experiment, the number of elements can be equated to a number of whole numbers, so that there is a first element, second element, third element, like this. And in that sense, it could be counted. But there are cases where the random variables is categorical in nature. Random variable is categorical in nature. Variables often called the dummy variable. A good illustration in this case, that is the example I'm going to provide you. Please try to listen to me carefully. Consider the sample space. Consider the simple condition in which the components are arriving from the production line. There is a production line, electronic components are being produced, and components are arriving on the production line, and they are stipulated to be defective or non-defective. As I told you, that when the component is there, it is defective or non-defective. Now, this production line is going on continuously for 1 year, 2 years, 3 years, without breaking, without any disturbance. Continuously, the electronic component are being produced, and every time you are going to check whether the product, whatever the electronic components is being produced, that component is either defective or non-defective. So that means you have infinitely many elements in your sample space. So at that time, I'm going to write my x in this way, that number of components are being produced, and in that case, my sample space random variable x, that is given in the form of 1 if component is defective, if the product or component is defective, and that is 0 if component is non-defective. So if you like this, if you write like this, the component is defective, that is assign the number 1, component is non-defective, it is assigned the number 0. So that makes perfect sense. Whenever you have infinitely many elements are there in your sample space, in your domain, at that time also you can assign the random variable, you can use the random variable x, and you can find your small m. Here your small m or small x is nothing but just 0, 0 and 1. Right? So random variable can be assigned for the infinitely many elements are there in this sample space too. That was not possible in the function. That is possible. So please keep in mind this thing, that so this is called the discrete random variable, because now you have this the example of discrete random variable, because you have first component, second component, third component, fourth component. You don't have 1.5 components. You can't say 2.5 components. You cannot say 5.7 components, right? They are just real natural numbers, or whole numbers, I would say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So that's why this is the example of discrete random variable. I'm just now bifurcating the terminologies of random variable in terms of the discrete and the continuous. So this is the example of a discrete random variable. So let me write down discrete random variable. Discrete random variable, an example of example of a discrete random variable, right? Like this, guys. Plenty of examples are there based on discrete random variable. And then after, now slowly I would like to move to the another part, and that is called the continuous random variable. So let me just go back again to the book, and I will let you know what we mean by the continuous random variable. Already I explained to you. Let me just give you brief idea. Continuous random variable, that means that is on the whole real line R, the real line, you can say R. That means suppose you have 0 somewhere over here, 1 somewhere over here, 2 here. That means you are counting each and every element between 0 and 1 without missing a single one. That means it includes the rationals as well as non-rational or irrationals. And you know this thing that between two rational numbers, suppose I have 1 by 2 and I have 1 by 3. So between two rational numbers, there are infinitely many irrational numbers. And between two irrational numbers, there are infinitely many rational numbers. That is the Dedekind-Kurz. Russian mathematician, he proved this thing, I think in 14th century, that between two rational numbers, you can find two consecutive rational numbers, I would say. There are infinitely many irrational numbers, and between two consecutive irrational numbers, there are infinitely many rational numbers. So this Dedekind-Kurz says that whenever you draw the real number R at that time, you're not missing a single number. Every number is counted. Infinitely many numbers are there, as I told you, but all the numbers are counted whenever we have this type of situation and that kind. And we define the random variable, suppose X. So this type of random variable, that is called the continuous random variable. So discrete means just you are going to get the number 0, 1, 2, 3, but in between nothing is there. 0, then 1, then 2, then 3, then 4, just like the production line, or the helmet example, 1, 2, and 3, like this. But continuous, that means you are not missing any of the numbers even between 0 and 1, 0.0001, 0.00002, 0.003, 4, 5, whatever it may be, all the numbers are included. So this type of numbers, that is called the discrete probability, it's a continuous probability distribution. So set of possible outcomes, that is uncountable. Here the possible outcomes, this is the possible outcome. This was the possible outcomes, and that was countable, right? We counted this 1, 0, 0, 1, 3 or 0, 1 possible outcomes, and they were countable. But now the set of possible outcomes is uncountable. So let me write it down. Set of possible outcome, small x, is uncountable. Set of possible outcome is uncountable. Right, guys? Set of possible outcome is uncountable. So that is called the continuous random variable. So this is the example of discrete and continuous random variable. So please keep in mind this thing, that now we are going to see the probability distribution. So probability distribution that is divided into two parts. One is the discrete probability distribution, and second one is continuous probability distribution. This discrete probability distribution, that is nothing but your article 3.2, and continuous probability distribution, that is nothing but your article 3.3. Once we are done with this article 3.2 and 3.3, then after we will be solving some examples. So very nicely defined articles are there. Look at over here, the 3.1 article, that is based on simply the random variables, what we mean by random variables, how it is defined, how it is associated with the function, domain, codomain, or sample space, and some numbers, set of possible outcomes, some numbers I mean to say. And then after your article 3.2 and 3.3, there is nothing but the discrete probability distribution and the continuous probability distribution. And then after we will be solving the examples as I told you. Okay, guys. So now let me go through let me give a couple examples based on continuous probability distribution, and then after we will be going through some other part. Okay, so let me again share my book. So that's what I have mentioned to you. Look at over here, the last example. Consider the simple condition in which the components are arriving from the production line and they are stipulated to be defective or non-defective. So you can write the random variable 1 if the component is defective or non-defective. So my possible outcomes are now simply 0 and 1 for the infinitely many items. Then after this is called the Bernoulli random variable. Whenever you write this 0 and 1 form like this is the special name that is called Bernoulli random variable. Bernoulli random variable. Statisticians are, then after I can go for another example, I think you can refer this example, very simple. Suppose the sampling plan involves the sampling items from a process until a defective is observed. Now look at here, the sampling plan involves sampling items from a process until a defective is observed. The evaluation of the process will depend on how many consecutive items are observed. In that regard, let X be the random variable defined by the number of items observed before a defective is found, right? Before a defective is found, with N, the non-defective, and D, a defective, sample space R, S is equal to, because we are just looking for the defective, so D with X is equal to 1. When X is equal to 2, your sample space will be ND. X is equal to 3, it would be NND, because you are looking for just one defective. For X is equal to 4, it is NNN, and then D. X is equal to 5, NNNN, and then D, like this. So this is, again, you can see the example of a discrete continuous variable. And now I would like to give you, this is my point, I would like to give you the next example. Interest centers around the proportion of people who respond to a certain mail order solicitation. Let X be the proportion. X is a random variable that takes on all the values X between 0 and 1. Right, so you can see here 0.001, 0.1, 0.0002, 0.5, all infinitely many numbers are involved over here. So between 0 and 1, it's just a real line. So this is the example of a continuous random variable. So let X be a random variable defined by the waiting time in hours. Now waiting time in hours, that means it could be 1 hour, 2 minutes, 5 seconds, 10 milliseconds. So you are measuring every number. Suppose it is between 1 to 5 hours waiting time. So between 1 to 5 hours or 0 to 5 hours, each and every number between 0 and 5 is being counted. And that's why this is the example of this waiting time period. That is the example of a continuous random variable. Continuous random variable. So read this one, that X be the random variable defined by the waiting time in hours between the successive speeders spotted by the radar unit. The random variable X takes all the values X greater than or equal to 0. As I told you, suppose it is 0 to 5, what number of waiting time, how many hours, we don't know. So in that case, we can say that is the example of a continuous random variable. Okay, so definition is, if a sample space contains the finite number of possibilities and unending sequence with many elements as there are whole numbers, it is called a discrete sample space, right? Finite number of possibilities means it is whenever it is countable, it is discrete sample space. Discrete sample space. And suppose you have, instead of finite, suppose infinite number of possibilities. Look at here, the sample space that contains the infinite number of possibilities equal to the number of points on the line segment, real line segment, I would say real line, that is called the continuous sample space. That is always the uncountable. This is countable, this one is uncountable. So just keep in mind this thing. So discrete random variable and continuous probability, continuous random variable. These are the two main concepts I just wanted to let you know. So now we are going to start, we are going to add the probability, because that is my main theme. Probability, how we define the random, how we associate the random variable or probability with the random variable. So first is discrete probability distribution. So how we assign the probability distribution with respect to the random variable. So first one is discrete probability distribution. Second one is continuous probability distribution. So that's what I would like to mention. Okay, discrete probability distribution and continuous probability distribution. Guys, now look at over here. Let me just go back and let me go for this one. As you know, this example. So how many outcomes are there? 1, 2, 3, 4, 5, and 6. 6 outcomes are there. out of these 6, how many zeros are there? For 2 items, JBS and BSJ. I'm again referring the example number 3.2. So for these 2 zeros, so total probability for this one is 2 out of 6. So it is 2 by 6. How many ones are there? 1, 1, and 1. So 3 ones are there. So total probability for this one, that is 3 times 1. So 3 divided by 6 is 1 by 2. SJB, how many outcomes are there? Just 1, that is 3 out of 6. So it is 3 by 6, that is equal to, or I would say just 1. So it is 1 by 6. Just 1, so it is 1 by 6, right? So here it is 2 by 6 because 2 zeros are there. 3 zeros are there, so 3 by 6. Just 1 times 3 is there, so 1 by 6. So I would like to write this one in terms of the probability distribution. Make sure whenever you are writing discrete probability distribution, you are going to make a table. That is not required for the continuous probability distribution. This is required only for the discrete probability distribution. So that's what we are going to learn now. That's what we are going to learn. So whatever the example I gave to you, I just would like to again go back to my screen so that you will have some more idea. Look at here. So first of all, as I told you that I want to, let me just change the color. Let me change this one and let me make a tabular form with respect to this example. So my M is nothing but this is my M and my probability distribution P, capital M is equal to small m. Now M is equal to 0. You can see over here I have 2 times 0. So for 0 and total sample space, that is 6. So it is 2 divided by 6. Then after I have 3 times 1. So 1 is 3 times, so 3 divided by 6. And then after I have 3. So 0, 1, and 3. 3 is just 1, so 1 divided by 6. So you can see here 2 divided by 6. That means I can write that is equal to 1 by 3, or I can write this one as 1 by 2, and this is 1 by 6. So that's what we mean by the discrete probability distribution. Discrete probability distribution. Now, frequently, so we will be using this table now later on, but before that, I would like to explain to you, I would like to give you the definition of a discrete probability distribution, and then after I would like to switch over to the continuous probability distribution, and then after go through some graphs. So first of all, let me go through the definition. Discrete probability distribution, that is always denoted by the order pair x and fx, because that is just a function. So it is given in terms of the order pair x and fx. Here it is given in terms of m and capital M of small m. So m and capital M of small m, or you can write f and x and fx. Both are equivalent. So let me skip this one and let me go back to, and you know this thing that whenever you find the probability at that time, if you take the sum of this probability fx must be equal to 1, because probability of sum of the probabilities must be equal to 1. And my third condition, that if I find the probability for x is equal to x or m is equal to capital M, that probability must be equal to my fx. So if these 3 conditions are satisfied, it is called the discrete probability distribution, or you can say probability function, or probability mass function, or probability distribution, right? So probability function, or probability mass function, or probability distribution. Let me again go back, guys, to my book, and it says something like this. Look at here. This is the example of that Smith, John, and Brown helmets, and we found the probability distribution like this. Number of outcomes and number of sample space m equal to, so that is this one. And the definition that a set of order pairs x and fx, order pair, that means you can consider x, small x on your x-axis and fx on your y-axis, so that you can plot the graph of x and y. So set of order pairs x and fx is the probability function, probability mass function, or probability distribution, whatever you want to say, of the discrete random variable. Please keep in mind this thing. This is a definition for a discrete random variable. For each possible outcome x, these 3 conditions are satisfied, that fx is greater than or equal to 0, probability of, or summation of fx must be equal to 1, because probability cannot be more than 1. It has to be exactly equal to 1 if you count all of them. And probability of x is equal to some particular x, that is equal to fx. That is equal to fx. So that's what we mean by this definition. And now let's go for this example. This example is really good example. Just read this one, and then after I will go back again to whiteboard. It says that a shipment of 20 similar laptop computers to a retail outlet contains 3 that are defectives. Now 20 similar computers, out of these 20, 3 are defectives. That's what we know. 3 are defectives. Question is, if a school makes a random purchase of 2, now school wants to buy just 2 out of this 20. What is the possibility? Find the probability or probability distribution for the number of defectives. It may be possible that whatever school are going to buy 2 computers, both of them are non-defective, or out of 2, 1 is defective, 1 is non-defective, or defective and non-defective, or it may be possible that both are defectives. Right? So these are the total number of outcomes. But whenever you are going to find this word, please keep in mind this thing, probability distribution. Find the probability distribution means we are talking about the random variable, probability assigned with the random variable, right? And here that is in terms of here laptops cannot be counted in terms of 1.5 or 2.7 or 2.3, something like that. It is a discrete probability distribution. So whenever probability distribution word is being used at that time, please keep in mind this thing that you are working with the random variable with respect to probability function with respect to the random variable. So that is the meaning. Okay, so now what is I want to find the probability distribution for the number of defectives. So please keep in mind this thing. Let me again share my whiteboard. Let me save this part. Save, and let me clear this one. Okay. So now, as I told you, suppose my first function f of 0. 0, I mean to say that no defectives. No defectives out of 2 laptops or laptop computers. No defectives out of 2 laptops. So my small x total outcomes are, or you can say total outcomes are, x is equal to either 0 because school is going to buy 2 laptops. It may be possible that none of them is defective, or 1 is defective, or both are defective. So what is the probability when x is equal to 0? So I would like to assign the function. This function is nothing but the random variable. This function is a random variable. So f of 0 that is equal to, look at here guys how I'm defining this one. First of all, f of 0 that means, let me erase this part. Okay. And f of 0. So this f of 0, I mean to say that I'm going to find the probability when x is equal to 0. And that is equal to, x is equal to 0. There are total 20 laptops out of 20. School is going to buy 2. And 0 means there is no defective. 3 are defectives. 3 are defectives. Out of these 3, because 0, none of them is defective. So my choice is 3C0. It's a combination problem. 3C0, chapter 2. 3C0. How many are left out of 20? Out of 23, where 3 are defective, but whatever school has bought, none of them is defective. That means all 2 computers, whatever they are going to buy from the non-defective parts, these are defective, these are non-defective. So that is equal to 17C2. So 17 plus 3 is 20. So 20 number is matching. 2 they are going to buy 2, they are going to buy. Separation, distribution is like this. Out of these 2, both of them are non-defective. And I mean to say that none of them is defective. So you can write this one as 3 factorial. So it is 3 factorial divided by 3 minus 0 factorial, that is equal to 3 factorial times 0 factorial. I'm using over here the combination formula chapter 2, n factorial over n minus r factorial divided times r factorial. Same here, if I write here 17, so 17 factorial divided by 17 minus 2, that is equal to 15 factorial and 2 factorial. And whole divided by, here it is 20 factorial divided by 20 minus 2, that is equal to 18 factorial and 2 factorial. So this is nothing but 3 factorial. 3 factorial is simply 1, so no need to write. And here it is 17 multiplied by 16 multiplied by 15 factorial. And here it is 15 factorial times 2. So this will get cancelled out, and here you are going to get 8. And divided by 20, 20 can be written as 20 multiplied by 20 factorial. So 20 multiplied by 19 multiplied by 18 factorial. Factorial will get cancelled out. 2 factorial is 2, and here it is 10. So 10 and 190. So it is, here it is 190. Here it is 190. So if you simplify this one, you are going to get that is equal to something 65, or I would say 140 divided by, or 136 divided by 190, right? So 136 divided by 190 divided by 190, and that is equal, I would say that is equal to 68 divided by 95. So that's how you can calculate. Then after, I have to go for f of 1, because now this is my random variable. 1 means 1 is defective. I have total number, that means my p probability, that is x is equal to 1 now, so 1 is defective. That means my total probability is 20C2, because out of 20 school is going to buy 2. But now out of 3 defectives, school is getting 1, unfortunately, from a random selection. So 1 is being selected over here. School is buying total 2 computers. 1 is already selected over here. So 1 is left out for in a group of non-defectives. So from non-defective, they are going to get 1. Again, use this NCR formula, and let me write down the answer directly. You are going to get 51 divided by 90. So, or 190, sorry, 51 divided by 190. Same way, I'm going to write f. So f of 2, that means p x is equal to 2, and that is equal to, now both of them are defective. So out of 3 defectives, 2 are defectives. That means non-defective portion from the part of non-defective, 0 is there, because all these 2 are being selected, because 2 are the maximum school is going to buy. So that is equal to, if you again use the same formula here, you are going to get that is equal to 3C2 and 3 divided by 190. 3 divided by 190. So these are my probability distribution function. So I would like to mention this thing in terms of, as I told you, that whenever you're working with probability, discrete probability distribution function, this is a discrete probability distribution function. So that is given like this. Here it is x. So 1 is, look at here, 1 is 0 is defective, or 1 is defective, or 2 are defective. And here I'm going to write x, yes please, x, and my f of x. So my f of 0 was 68 divided by 95, and then after 1, so it is 51 divided by 190, and then after it is 2, so here it is 3 divided by 190. So this is my distribution function, and this is the table, right? Now, sometimes you may have, I would like to extend the same idea. The example is over, but I would like to extend the same idea for a cumulative distribution function, cumulative probability distribution, because here it is, I've counted f of 0, then after I counted f of 1 separately, f of 2 separately. But suppose I want to join this f of 0, 1, and 2. F of 0, 1, and 2, how they are related, or if you want to add, suppose, is it possible that you can add 68 and 95 plus this one, or this plus this plus this one? That is called the cumulative distribution function. So let me go for the definition of a cumulative distribution function. The cumulative distribution function, and that is given by capital F of x. This is the symbol. Please keep in mind this thing, of a discrete random variable, capital X, with the probability, distribution fx is capital F of X is equal to P. Now look at here, X is less than or equal to X, because we are counting X is equal to for 0, then we are going to add 0, then 1, then 2 all together. So that is equal to summation of F of T, where T is less than or equal to X. So that is called the discrete probability distribution. Discrete probability distribution. You know this thing from our previous table that Smith, John, and Brown helmets. So this was the order and it was 3. So again, I would like to write the same thing. M is equal to correct order. So, and correct order, that was 3. 0 and 1, these were my total outcomes. So my P, capital M, is equal to small m, that was 2 times 0 were there. So 2 divided by 6, that was 1/3, 1 by 2, and 1 by 6. 1/3, 1 by 2, and 1 by 6, right? As per example. So suppose I want to find F of 2, capital F of 2. So that means that is equal to probability of capital X less than or equal to 2. Less than or equal to 2. Capital X less than or equal to 2. Look at over here, less than or equal to 2. I have 0 and 1. There is no 2. That means it is F of 0 plus F of 1. That is the meaning. T less than or equal to, so T is first 0 and then 1. So F of 0 and F of 1. F of 0 value is 1 by 1/3. F of 2 value is 1 by 2. That is equal to 5 by 6. So that's what we mean by the cumulative function, and that is F of 2. Cumulative function F of 2. Cumulative distribution function F of 2. Right? So in general, suppose I want to write, let me again change the color. In general, suppose I want to write my F of capital M. F of capital M. So this F of capital M, I'm going to write, this is my in general. I just found here F of 2, but I'm going to write F of M, capital distribution, cumulative distribution function F of M is given in the form of when M is less than 0, it is 0. When M is less than 0, because less than 0, nothing is there, so it is 0. Now between 0 and 1, because I'm talking about M is less than 0, now between 0 and 1. So I'm going to write like this. Now 0 is less than or equal to M, and that is strictly less than 1. So 0 is less than or equal to M, and that is strictly less than 1. So 0 equality is there. Now equality makes sense for the cumulative distribution function, but in future we are going to learn cumulative continuous function, continuous random variable. In that case, this equality doesn't make sense. I mean, to say equality, we just ignore it, because anyhow we are going to go up to that point. I will let you know. So 0 is less than, because equality is there and value is 1/3. So I would like to write here 1/3. 1/3. Then after 1 is less than or equal to M is less than, now 1, and then next value is 3. So that is less than 3. So 1 is less than or equal to M, and so it is now 1/3. 1 is equality is over here 1 by 2. So it is 1/3 plus 1 by 2, and that is equal to 5 by 6. So that is equal to 5 by 6. And that's what my F of 2 was. F of 2, that is 5 by 6. Anyway, and then after 3 is less than, now I don't have any other choice. So 3 is, you cannot say, so let me write M is greater than or equal to 3. Because nothing is there, M is now greater than or equal to 3. That means for equality, I have 1/6. So I'm going to write these numbers, all these numbers. So let me write 5 by 6 plus 1/6, and 5 by 6 plus 1/6, that is 6 divided by 6, and that is always 1. So my first number will always, because that is M less than 0, always 0. And my last number must be always equal to 1, because my definition says that summation of fx must be equal to 1. So last number must be equal to 1. In between, you have to add the numbers and try to figure it out things. Right, guys? Now let me remove some of the portion over here so that I can explain to you, because I'm going to use the same example for the graphs. So how can we plot the graph? So that's what I would like to know now, let you know. Or we can go for one more example, or I can go for the graphs of the same function. So let me erase this part. So erase, and because now you are well aware of this one, so let me just erase this one. Okay. Okay, guys, so let's go for this one and this one. So let me draw this line. And suppose I have the same values over here and I want to plot a graph. And this graph is something like this. Suppose I have, once you have cumulative distribution function and your cumulative distribution function starts with 0. So I would like to write something like this. Suppose here it is 0, and then after, or let me write some number. Suppose let me put something like this, and here it is 0, and then after I would like to mention somewhere over here 1 and somewhere over here 3. So this is nothing but my m, and this is nothing but my capital F of m, continuous, so I'm going to say cumulative distribution function. And you can see over here my m values less than or equal to 0. That's why I put this line. So less than or equal to 0 value is 0. So let me just put something like this. Less than, of course, 0 starts with here, but I wanted to let you know that less than or equal to 0, m less than or equal to 0, this portion. So that's why this is the line, and less than or equal to 0. So let me put this point is included and this one is excluded. Then after, if I go for suppose between 0 to 1, you can see here value is 1/3. So let me now write some of the things. Suppose here it is 1/6, and then after somewhere over here, suppose it is 1/3. Somewhere over here, suppose it is 1/2, and somewhere over here, I have 5/6, something like this, right? So between 0 and 1, I have 1/3. So 1/3 is over here. So here it is 1/3. So this is now included because value is 1/3. Equality, this is included, this is equality. So that's why I included that point, and this part is open. So I would just I don't want to include this part. So let's just leave like this, or you can put something like this. Okay, and then after I would like to go for the next point. So next point you can see over between 1 to 3 value is 5, 6. So 1, 2, 3 value is 5, 6. So I can go up to here, and this one is included, and 1, 2, 3 value is 5, 6. So this one is eraser, and just let me erase this part. And okay, so 1, 2, 3, this is my, and value is 5, 6. Value is 5, 6, right? So this way you are getting a kind of, you can say step function, or you can say like this. Suppose this is the value, so you can just plot the numbers, plot like this. For here you were getting something like this. For here, right, that was I think I don't want to mix up this part, so let me just remove this one. And let me remove this one. Okay. Okay. So this is f of, and this one. And suppose now I would like to go for this one, whatever exactly we have. I just would like to go for my x, or you can say m and f of m, small f of m. Look at here. F and small f of m. So m is equal to, let me write over here, suppose 0, and here it is 1, and here it is 3. And f of m, that was nothing but this one. So it is 1/3. So here it is 1/6, then after 1/3, then after 1/2, and then after 5/6. So for 0, it is 1/3. So this is the number. So that's why I would like to plot this dotted line. This is the number. Then after, for 1, I have 1/2. So 1/2 is somewhere over here. So I would like to plot the dotted line like this. And for 3, I have 1/6. So I have 1/6. So that is the line. So I would like to plot like this. So this is the probability mass function plot. Probability mass function plot. This is the cumulative probability distribution. Cumulative probability distribution, right? And I can exchange the same idea for the histogram for this probability mass function, I can plot the histogram also. So I have again, suppose 0 over here, 1 over here, and here it is 3. So here it is 1/6, and here it is 1/3, and here it is 1/2, and here it is 5/6. Here it is, sorry, 5/6, and f of m. F of m. Okay, so whenever you plot this one, you know this thing that usually we start like this. So if you have 0 over here, so let me take some value, just side to 0. And here it is for 0, what is the value I have? 1/3. So here, and then after I can take the middle of this one. Then after, or you can start, you can draw the picture over here too. Suppose I want to change the color. Then for histogram, you can do something like this. Like this, and then after you can go over here and you can go like this, and you can go to the middle of this one, and then after you can go like this and you can go to the middle of this one. So this is the histogram. This is the histogram also. So you can plot some separately like this, some separately like this, or you can plot. So this is the histogram. This is the histograms. Discrete probability, sorry, cumulative discrete or discrete cumulative distribution, cumulative discrete actually, cumulative discrete distribution, that's always a step function, and this is always, this is the histogram. So your FM, X to FM or X to FX, M to FM, that will provide you the histogram, or you can say the dot product, dot line, dotted line, but the cumulative distribution that will provide you always the step function. Please keep this thing in mind. And now we would like to start with the continuous probability distribution. So my next part is continuous probability distribution. Let me just erase this part. This part is already done. So let me save this one. Save this one. And now let's clear this one. And now I would like to go for the article 3.3. So 3.3 says the continuous probability distribution. Continuous probability distribution. Continuous probability distribution, that means always you will be having something like this, because that is all above the x-axis. So the continuous random variable has a probability of 0 of assuming exactly any of its values. So consequently, its probability distribution cannot be given in a tabular form, right? So now we are not going to give this one in the tabular form. Also keep in mind this thing that we shall concern ourselves with the computing probabilities for various intervals of continuous random variable. Various interval of continuous random variable, I mean to say that various interval of continuous random variable, that means suppose now probability of A is less than X is less than or equal to B. There is nothing but probability of A is less than X is less than B plus probability of X is equal to B. Probability of X is equal to B, and there is nothing but probability of X is less than or equal to, A is less than or equal to X is less than B. And because you can see both are same, and that's why I told you that equality doesn't matter over here. Anyhow, we are going to count that point. So that is, it does not matter whether we include an endpoint of the interval or not. So that doesn't matter. So please keep in mind this thing. I repeat, it doesn't matter if we include the endpoint or not. If we include the endpoint or not for the continuous probability distribution. Please keep in mind this thing. Okay, and or not. And for discrete case, that was not true. So please keep this thing in mind too. So although the probability distribution of a continuous random variable cannot be presented in a tabular form, as I told you, it can be stated as a formula. So we have to have some formula for this one. Such a formula would necessarily be a function of the numerical values of the continuous random variable X, capital X, and such will be represented by the function of f of X. And in dealing with continuous variable, fx is usually called the probability density function. Previously, it was probability mass function for the discrete case. For continuous case, it is called the probability density function. Probability density function. And some people, they say this one as PDF, probability density function. It is known as PDF also. Probability density function and function of capital X, of course. And since X is defined over a continuous sample space, it is possible for fx to have a finite number of discontinuities. So because areas will be, and that means it represents some area, and because areas will be used to represent the probabilities, area cannot be negative. That means it has to be above the x-axis. So because the areas will be used to represent the probabilities, and probabilities are positive numerical values, probability cannot be less than 0 or greater than 1. So density function must be entirely above the x-axis. So density function, this density function that is always above the x-axis, above x-axis, always above the x-axis. So you may have some figure like this above x-axis, or you may have, suppose, something like this, or you may have some normal distribution like this, or you may have something like this. So the probability density function is constructed so that the area on the curve, its curve is bounded by the x-axis, and that is always equal to 1. So area under the curve, this is suppose x is equal to a and x is equal to b. So this area, this represents the area, and that area under the curve must be equal to 1. Must be equal to 1. Area under the curve must be equal to 1. That means if I want to write probability of x is less, sorry, my bad, a is less than x is less than b, then that is equal to integration of fx dx, where x is equal to a to b. Integration of fx dx, x equal to a to b. That means suppose I have some normal distribution curve, something like this, and suppose I have x is equal to a somewhere over here and x is equal to b somewhere over here, and this is the area we are going to find, and this area must be equal to 1, and that leads us to define the probability density function. And probability density function definition is, of course, my first condition, fx must be greater than or equal to 0. Second condition, that integration negative infinity to infinity of fx dx must be equal to 1. And my third condition is probability of a less than x less than b, that is equal to integration a to b fx dx. So whenever these three conditions are satisfied, in that case, we can say that that is a probability continuous or continuous probability distribution function or probability density function. Probability density function. Let me save this folder. And now let me again clean this one, and let me share my book so that you will have a little bit more idea now. So in the book, it says exactly the same thing which I defined, which I explained to you. Look at here, guys. And now this is the definition. So function fx is a probability density function PDF for the continuous random variable x defined over the set of real numbers. Not a single number is missing. If fx is greater than or equal to 0, negative infinity to infinity fx is equal to dx equal to 1, a is less than x is less than b, that is equal to a to b fx dx. Right? If these three conditions are satisfied. Look at this example number 3.11. And in this example says that suppose that the error in the reaction temperature in centigrade for a controlled laboratory experiment is a continuous random variable x having the probability density function fx equal to x squared by 3 in the range of -1 to 2. Otherwise, it is 0. -1 to 2, once you write, that means you don't have to mention -1 is less than or equal to x, or -1 is less than x is less than or equal to 2. As I told you, equality, anyhow, we're going to count that point. Verify that fx is the density function. That means you have to verify that fx satisfies these three conditions, density function. And the second point is find 0 is less than x is less than or equal to 1. Find the probability of the random variable x between 0 and 1. So that means between 0 and 1, that means you need to change the range between 0 and range of the integration between 0 and 1. So again, let me just go back to my whiteboard to solve this example, and that will give you more idea. So let me go through this one and let's start with this example. So my example says that first, but please keep in mind this thing, verify that fx is the density function. That's what we are going to define. We are going to verify this thing. And then after we're going to find the probability density function between 0 and 1. So let me stop sharing this book again. And I would like to go for this simple integration, your calc 2, I would say. So my function here is fx is equal to x squared by 3, -1 is less than x is less than 2, and here it is elsewhere, and that is equal to 0. My first part is fx is a density function. That's what I want to verify. Fx is a continuous density function, I would say, density function. So integration -∞ to infinity of fx dx, that is equal to -∞ to, my interval is like this, see, -1 plus -1 to 2 plus 2 to infinity. But we don't have anything for, so this is 0, this is 0, right, and dx. Here I have a function x squared by 3 and dx. So that is equal to 1/3 is out and x cubed by 3, and here it is -1 to 2. So that is equal to 1/9, and here 2 cube is 8 minus -1 cube is, yes please, 2 cube is 8 and minus -1 cube is -1. So that is equal to 8 and minus 1. So that is equal to 9 divided by 9, and that is equal to 1. See, I'm getting 1. So that means it's a density function, because density function means area must be equal to 1. And my B part says that find probability of 0 less than x is less than or equal to 1. So in integration, now just I need to change this one, 0 to 1 and x squared by 3 dx. Again, it is 1/3, and here it is x cubed by 3 and 0 to 1. So that is equal to 1/9. So this is the probability between 0 to 1. Probability between 0 to 1. So that's how you can solve the example. And now I would like to go for one more example before we start the or same thing. So I'm not going to write this thing. Let me just use the book. Let me just use the book and look at here. Now, the next definition, that is for the cumulative distribution function. So cumulative distribution function, but for the cumulative continuous distribution function. So you just add one word over here. It is cumulative, but for continuous, or cumulative density function, you can say. Cumulative distribution function or density function. Again, that is, it's the first fundamental theorem of calculus, very similar to this, that theorem. Fx is a continuous random variable x with the density function fx. Then f of x is x less than or equal to x. Now it changes -∞ to x ft dt. Previously it was summation of ft dt and t less than or equal to x. Now it is -∞ to x ft dt. And my previous example, suppose I want to find f of b and f of a, right? So if you write f of b and f of a, that is nothing but this one, just the reverse case of integration and derivative. So, okay, so in my previous example, if I want to find, I found 0 is less than x is less than or equal to 1, and that was 1/9. For -1 to 2, what will happen? For -1 to 2, I want to find capital of fx, -1 to 2. So capital fx is by definition -∞ to x ft dt. -∞ to x ft dt. This -∞ to x is divided into number of parts, but my function is only defined between -1 to, look at here, my function is defined only between -1 to 2, and that is x squared by 3, otherwise it is 0. So no value. So same here, my function is defined only between -1, so x squared by 2. I think it is better if I write it down for you. So just please try to understand this one. So this is the thing I'm going to find fx and use it to evaluate, find fx. First of all, I need to find fx, means cumulative density function, cumulative distribution function. That's what I'm going to do. I'm going to use the definition given over here. -∞, sorry, this one, negative infinity to x, ft dt, ft is t square by 3. So 1 by 3 is out and t cube by 3 is the integration, and negative 1 to x. So it is x cube plus 1 by 3. X cube plus 1 by 3. And I want to find this one. Using this one, I'm going to write the 0 is less than x is less than or equal to 1. So please keep this example in mind, and let me stop sharing this one and let me share my whiteboard again. So if I share my whiteboard, look at here. So my f of x, cumulative density probability distribution function. So f of x is equal to negative infinity to x and f of t and dt, and that is equal to negative infinity to x and f of t, that is equal to t square by 3 and dt, that is equal to 1/3 is out and t square is t cube by 3 and negative 1 to x. So that is equal to x cube minus 1, right, divided by, or minus plus, so divided by 9. That is f of x. And therefore my fx now I can write in the f of x, I can write that is in the form of, if x is less than negative 1, value is 0. If negative 1 is less than or equal to x is less than 2, negative 1 to 2. Negative 1 to 2, negative 1 to 2. If you replace this x by 2, so 2 cube is 8 plus 1, 9, right? So negative 1 to 2, if you replace by this one. But in between negative 1 to 2, your value is this one, x cube plus 1 by 9. Negative 1 to negative 1 to 2. So negative 1 is less than or equal to x is less than or equal to 2. Value is x cube plus 1 divided by 9. X cube plus 1 divided by 9. And if I take x is greater than or equal to 2, value has to be just equal to, because cumulative, so if you add this one, whatever you're going to get, you can add over here, and that value must be equal to 1. That value must be equal to 1. Our next step is, you need to find now, we need to find 0 is less than, x is less than or equal to 1. So that is equal to f of 1 minus f of 0. F of 1, that is always written like this, f of 1, because probability of a less than x is less than b, that is equal to f of b minus f of a. That's what is given to you, f of b minus f of a. So this is equal to, now f of 1, you can see that is somewhere over here. F of 1 lies over here, right? So f of 1, that is nothing but, yes, f of 1. If you replace this one by 1, so 1 plus 1 is 2, 2 by 9, so it is 2 by 9. And f of 0, yes, please, so f of 0 is nothing but, what is f of 0? If you write f of 0, x is replaced by 0, it is 1 by 9. So that is equal to minus 1 by 9. So that is equal to 1 by 9. So my probability between 0 and 1, or cumulative density probability between 0 and 1, that is 1 by 9. That's how you can solve this example. One more example is there in the book. You can solve by yourself, or you can do something, or let me just stop over here, because I think already I took 1 hour and something. So I can take one small class so that we can finish examples, or I think let me continue. I think that's the good idea. So I can finish the examples very quickly. Now, this is the book. So let me just save this one. Okay, clear. So let me clear this part, stop sharing, and you have a book. So please try to refer the book. You have a book. So please, where I was. Okay, so look at over here, guys. So it says that classify the following random variables as discrete or continuous. The number of automobile accidents per year in Virginia. So it could be maybe, suppose 5 accidents or 500 accidents, 1000 accidents or 1200 accidents, something like that. But it is always a fixed number, so it's a discrete. The length of time to play 18 holes of a game. Length of time to play 18 holes of a game. So that is again continuous. Then after, the amount of milk produced yearly by a particular cow. So it could be 1 gallon, 2 liters, 5 milliliters. So it could be any number in a continuous real line. So it's a continuous variable. Number of eggs laid by the each month by a hen. So you cannot say 1.5 egg. It's 1, 2, or 3, something like that. The number of buildings permits. So it's a discrete. The number of building permits issued when the month in a certain city, right? So number of permits issued, that is either 1, 2, 5, but it's not 5.2. So it's a discrete. The weight of a grain produced per acre. So that is always, because it's a continuous, so it is continuous term, because it could be anything, right? It is 100 quintal, 100 tons, and 5 quintal, and 1 kilogram, and 200 grams, and something like that. So it could be any number. Okay, guys. Now, example number 2 says that, or let me go through example number 3. I think that is a good idea. So example number 3 says that, because I would like to consider this example 3 with example 3.8 and 3.23. All 3 examples together, that will give you complete idea about all these 3 articles. First of all, let's see all these 3 examples together. 3.3, 3.8, 3.23. Let W be a random variable giving the number of heads minus the number of tails. Number of heads minus number of tails. Suppose you have 3 heads and 1 tail. So 3 minus 1 is 2. That's the meaning. So please keep in mind this thing. Try to pick up the words. The number of heads minus number of tails in 3 tosses of a coin. So 1, 2, and 3 tosses of a coin. So first of all, you need to write sample space. So all 3 are heads, or 2 are head and 1 is tail, or 1 head, 1 tail, 1 head, or 1 tail and 2 heads. So there are 8 different possibilities, and we are going to assign the total number of outcomes in terms of 1, 2, negative, whatever it may be. Okay. List the elements of the sample space as for the 3 tosses of the coin to each sample point assigned. So we have to make a tabular form. Okay, we will do this thing. Then after, I would like to switch over to example number 3.8. It says that find the probability distribution of the random variable W in the previous example 3.3, which just I read it. Okay, so now we would like to define the probability distribution of the random variable. Assuming that the coin is biased so that the head is twice as likely to occur as tail. Okay, again 2 and 1. So the head is as likely to occur twice. So 2 times head and 1 time tail, something like that, right? 2 times head and 1 time tail. That is 3.8. So here we are going to find the probability distribution of the random variable W, assuming that for the same example, the coin is biased so that head is twice as likely to occur as a tail. Okay, and the last one, 3.23, all 3 examples I'm going to take together, and you will come to know the differences. Find the cumulative distribution functions. Now we are looking for the cumulative distribution function of the random variable W in the previous example 3.8 using f of W, find W greater than 0, negative 1 is less than W is less than 3. Now I think you realize this thing why I chose these 3 examples, because that consider article 3.1, 3.3, 3.1, 3.2, and cumulative part, all these things simultaneously for the discrete random variable. 3.1, 3.2 for discrete random variable or mass function, and the probability for the cumulative function. So all these 3 examples in 3 different forms. Okay, guys, so I think you understood these 3 examples, and now let me just go back to the first example, 3.3. Let W be a random variable giving the number of heads minus number of tails. So I'm going to write the sample space for this one and total number of outcomes. Okay, let me start with this one. So let me share my screen. And if I share the screen, I'm going to write first of all 3.3. So example 3.3, page number 91 of a book, page number 91. So we are going to take 91, then 92 and 93. Okay, guys. So page number 91 of a book. Okay. So first of all, let me write this one. This is in the form of sample space. So let me write sample space, and let me write W. Let me write W. All H, and H. First of all, let me write the sample space H, and T, H, T, and H, T, or H, T and H, T, H and H, then T, or I can write H, T and T, H, T and T, T, H and T, then T, T and H, and then T, T and T, T, T and T. Okay. Number of head minus number of tails. Number of head minus number of tail. So no tail, so here it is 3. 2 minus 1, it is 1. 2 minus 1, 1. 1 minus 2, sorry, number of head minus number of tail. So it is again 1. Then after, number of head 1 and 1 minus 2, negative 1. 1 minus 2, negative 1. 1 minus 2, negative 1. And here it is negative 3. So these are number of outcomes, total outcomes. Total outcomes. So that's what your example 3.3. And now my next example, as I told you, that is 3.8. So next example 3.8, I just would like to go like this. For 3.8, what will happen? Look at here, let me change the color just for your convenience. So now example 3.8, because they all three are in sequence. So refer to the sample space, but now you have to make sure that heads are twice as likely to occur as tail. So head are twice as likely to occur as tail, right? So probability of head is equal to total 3 times, right? Head are as likely to occur as tail means it's 2 by 3. And probability of tail, that is equal to 1 by 3. That is equal to 1 by 3. So if I write probability of, suppose W is equal to negative 3. Negative 3. Let me start with this number. W equal to negative 3. So that is equal to probability of T, T, and T, and probability of T is 1/3. 1/3. Probability of another T, 1/3. 1/3. So it is cube. So that is equal to T, T, and T. So that is equal to 1/27. Then after, let me go for probability of W, and W is equal to now negative 1, right? Negative 1, because the second number is negative 1. My W space set contains negative 3, negative 1, 1, and 3. Negative 3, negative 1, 1, and 3. So W is equal to negative 1. So that is equal to W equal to negative 1. So probability of, you can see these 3. HTT, HTT, plus probability of THT, plus probability of TTT or TTH for negative 1. What will happen? Probability of H is 2/3. Probability of T is 1/3. And T is 1/3, so it is square. So T is 1/3. So that is equal to square. Same here. Probability of T is 1/3. T is 1/3, so square. And H is 2/3. So same thing. So again, the same part. So let me write 2 here. Probability of T is 1/3. Probability of T is 1/3. So square. And probability of H is 2/3. So total 3. Total 3. So that is equal to, if you simplify this one, you're going to get that is equal to 2/9. That is equal to 2/9. Now let me go for probability of W is equal to 1. W is equal to 1. So that is equal to probability of 1 appears over here for these 3 times. So probability of H, HT, plus probability of HTH, plus probability of THH. THH. Probability of H, that is 2 by 3 n square, and probability of T is 1/3. Same here, same here. So 3 times. So that is equal to 4 by 9. That is equal to 4 by 9. Finally, probability of only this 3 is left out. So W is equal to 3. So that is equal to probability of H, H, and H. And that is equal to probability of H, 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 that is equal to 2/3. And here it is cube. So that is equal to 8 by 27. 8 by 27. So naturally, my probability distribution function, we have to make the table because it's a discrete. So probability distribution for capital W is now small w and P W is equal to small w. So here it is -3, then -1, then 1, and then 3. This is my table now. One and 3. So that is equal to 1 over 27, right? 1 over 27, then after 2 over 9. So 2 over 9, then after 4 over 9, and finally it is 8 over 27. 8 over 27. So that is the example number 3.8. And now I would like to change the color for the next example. So my next example is, I said it is 3.23. So 3.23 says something like this. 3.23, I think so. Which number I gave you? 3.23. Yes. So my 3.23, that is the cumulative probability distribution. So example 3.23. The cumulative distribution function of x is given by f of x is equal to right guys. First of all, w is strictly less than -3. W is strictly less than, because -3, -1, 1, and 3, these numbers are there. So -3, so that is equal to 0. Then -3 is less than or equal to w is less than -1, right? -3 is less than or equal to w is less than -1. So w is equal to -3. I had 1 over 27. So 1 over 27. Then after -1 is less than or equal to w is less than 1. So this plus this now. So it is 1 over 27 plus 2 over 9. And that is equal to 7 over 27. 7 over 27. And then after 1 is less than or equal to w is less than 3. So that means it is now 7 over 27 and now one more. So it is 4 over 9. 4 over 9. So that is equal to 19 over 27. And finally, w is greater than or equal to 3. So that means now I have 19 over 27 and I have to add this last part. So that is equal to plus 18 divided by 27. And that is equal to, if you add this one, 19 plus 18, 27 plus 27, that is equal to 1. I told you first one is 0, last one must be equal to 1. So my A part now says that probability of capital W greater than 0. So that is equal to, now probability of capital W greater than 0, that can be written as 1 minus probability of W less than 0. 1 minus probability of W less than 0. That is equal to 1 minus probability less than 0. Less than 0. You can try to figure it out. Less than 0, that lies somewhere over here, right? So less than 0, that is somewhere over here in this portion. So that is 7 over 27. So 1 over 7 over 27, and that is equal to 20 divided by 27. That is the answer for this part. B part says that probability of -1 is less than or equal to W and is less than 3. So that is equal to, now -1 is less than W is less than 3. So I can write the same part in the form of f of 3 minus f of, it's a cumulative distribution, right? So f of -1. F of -1. F of 3, you can see here, f of 3 is nothing but, yes please, f of 3 that lies over here. So it is 19 by 27. 19 by 27 minus f of -1. F of -1, that is nothing but -1, that is 1 over 27. So 1 over 27. So my answer over here would be f of 3 and f of 1 minute. Let me verify. So f less than 3 and x less than or equal to -1. Let me write this one in a separate form. So clear. Not clear, I want to go for eraser. Okay. Okay, so this can be written as probability of 3, or you can say x is less than 3 minus probability of x less than or equal to -1. X is less than 3, that is equal to f of 3 minus f of -1. That is equal to 19 by 27 f of 3, right? F of 3, that is equal to 19 by 27 minus, you can write 1 over 27, and that is equal to 2 over 3rd. So this is the answer for the third question. So that's how you can solve the number of examples given over here. Plenty of examples are there given here. I solve these 3 examples, and then after we can go for last example, and then we will stop. So last example is something like this. Let me go for which one? I think all of them are just easy, but let's go for example number, suppose 3.11. So let me save this one and let me clear the picture. Let me stop sharing and let me share my book again for the last example almost. Let's go for 3.11. It says that a shipment of 7 television sets contains 2 defective sets. A hotel makes a random purchase of 3 of the sets. If X is the number of defective sets purchased by the hotel, find the probability distribution X. Express the results graphically as a probability histogram, right? As a probability histogram. So this example is quite simple because we already did this type of example, but if you want, I can go for this one. It's not that difficult. Only thing is shipment. So we need to first define the function. So just keep this example 3.11 in mind, and let's share the screen again. So let's share the screen. 3.11. Example 3.11, it says we can select X as a defective sets from 2. So X is the defective set, you can say, or defective sets from 2. So naturally 3 minus X, that is the good items or good sets, good item sets, good sets from 5. Right? So my fx, what is my function? My function will be out of total. I read the example. Shipment of 7 televisions contains 2 that are defective. So out of 7 that contains 2 are defective. Hotel makes a random purchase of 3 television. They are choosing 3. If X is the number of defectives televisions, the number of defectives, okay. Purchases by the hotel, find the probability distribution function. So naturally, how many are there? So 7. Out of this 7, hotel makes a random purchase of 3. So out of this 7, 3 are being purchased. And then 2 are defective. So if 1 is defective, it is 2CX, right? And 2 are defectives. So naturally 3 minus X, that is non-defective. Out of how many? Out of it is 5. So 5 and 3 minus X. 5 and 3 minus X. If you take F is equal to 0, then X is equal to, they are going to select 3, right? So, sorry, 2 are defectives, and express the distribution of X. If X is number of defective televisions purchased by the hotel, find the probability distribution of X. Okay, so F of 0 and then F of 1 and F of 2. These 3 you can try to figure it out. And if you plug the values over here, F of 0, so F of 0 will be 2C0, and here it is 5C3, and here it is divided by 7C3. 7C3. So you're going to get one number, and that number will be 2 over 7, if I'm not wrong. And then F of 1, again it is 2C1, and then after 5C2 and divided by 7C3. And that is nothing but 4 by 7. And the third part is 2C2, and then after 5C1, and then after this is F of 2. F of 2. And then 7C3. 7C3. So that will be equal to 1 over 7. 1 over 7. Right, guys? So I can make a tabular form like this, and that tabular form will provide us, this is my x, 0, 1, and 2, and this is my fx. So I can write 2 over 7, 4 over 7, and 1 over 7, and 1 over 7. And I want to plot the histogram. That's what it says. So usually we start like this. This is suppose 0. Right, or I can write 1, 2, and 3. Just wait, guys. So here it is 0 and x is equal to 0, 1, and 2. Okay, fine. So x is equal to, let me write 0, 1, and 2. And 2 over 7. So somewhere over here I have 1 over 7. Somewhere over here I have 2 over 7. Somewhere over here I have 4 over 7. So 0 and 1, for 0 I have 2 over 7. So this is the point. Okay, then 1 I have 4 over 7. I have 4 over 7, and 2 I have 1 over 7. So 2 I have 1 over 7. So if you plot this graph, you are going to get something between 0 and 1. So this is the histogram. So this is the example histogram. And then after the last portion, if somebody wants, let's go for example number 3.17. It says that 3.15 is in the continuous sum. So I think somebody can solve 3.15 because they both are in continuous sum. 3.15 is just easy. 3.15. If because 3.15 there's a cumulative function, so cumulative function will be given fx is equal to, we need to find the cumulative functions. If x less than 0, it is 0. If 0 is less than or equal to x is less than 1, here it is 2 over 7, and then 1 is less than or equal to x is less than 2, then it is 2 over 7 plus 4 over 7, so that is equal to 6 over 7. And finally, x is greater than or equal to 2, in that case you're going to get 1, because if you add this 7 over 7, that is equal to 1, right? And a part says that the probability x is equal to 1, that is equal to probability of x less than or equal to 1 minus probability of x less than or equal to 0. So that is equal to 6 by 7 minus 2 by 7, right? And that is equal to 4 by 7. And my b part for this example 3.17, that is b part is equal to probability of 0 is less than x is less than or equal to 2, that is equal to probability of x less than or equal to 2 minus probability of x less than or equal to 0, and that is equal to 1 minus 2 over 7, and that is equal to 5 over 7. That is equal to 5 over 7. So that's how you can solve this example. And last small portion, and let's stop here because it's a long class today, almost 1 hour, almost 2 hours. So 3.17, that is the continuous CDF, continuous density function. And that says that 3.17 and 3.19, they are same. A continuous random variable x that can assumes values between 1 and 3 as a density function given that fx equal to 1 by 2. Okay, so that the area under the curve is 1, so fx is equal to 1 by 2. And you are asked to show that the area under the curve that is equal to 1. So you can say, and that is between 1 and 3. So integration is 1 to 3, and fx is equal to 1 by 2 and dx. So that is equal to x by 2 and 1 to 3, and that is naturally equal to 1. This is my a part. My b part says that probability of 2 is less than x is less than 2.5. So that is equal to integration because a continuous function. So 2 to 2.5 equality doesn't matter, and ft dt. ft dt or dx. So that is equal to x by 2 if you want, right? X doesn't matter. So 2 to 2.5, and that is equal to 0.3. And finally, C part is probability of x is less than or equal to 1.6. So that is equal to integration x is equal to 1 to 1.6 and 1 by 2 into dx, and that is equal to x by 2 and 1 to 1.6, and that is equal to, I think this is x1 by 2, 1. So it is 0.3. I think this is wrong. So 1, 2, and 2 minus, so 2 minus 1 is 2. So 1 by, so it is 1/4. So it is 1/4. So that's how we can go for the example number. I can erase this portion if you want. I can erase this portion if you want. And because let's make a 2 class combined over here, 2 classes, right? Because almost it's 2 hours. So let's finish this 2 hours and try to stop it over there. Okay, guys. So that is about example number 3.17, and now 3.19, the last one. I promise this is the last one for today. So 3.19 says for the same density function, this is in continuation, 3.17 and 18. That's why I took this one. For the density function for exercise 3.17, find fx, cumulative continuous density function. Used to evaluate, find fx, what is fx, and then used to evaluate p, 2 is less than x is less than 2.5. These 2 items we need to find. Okay, not a big deal, because here it is f of x. So for 1 is less than or equal to x is less than 3, my capital of fx will be 1 to x by definition and 1 by 2 into dx. And that is equal to x minus 1 divided by 2. X minus, so my fx will be, my f of x will be 0 if x is less than 1. 1 is less than or equal to x is less than 3. The value is x minus 1 by 2. And if x is greater than or equal to 3, value is 1. And finally, I am asked to find, this fx is done. A part is done. This is my A part. And my B part says that 2 is less than x is less than 2.5. That is equal to, by formula, f of 2.5 minus f of 2. F of 2.5, that is naturally 1.5 by 2, right? Because f of 2.5 minus 1, that is equal to 1.5 minus 2 minus f of 2. So 2 minus 1, that is equal to 1 by 2, right? 2 minus 1, that is equal to 1 by 2. So that is equal to 0.5 by 2. And that is equal to 1/4. And answer. So this is the end of today's class. Thank you so much, guys, for your patience. I know I should have prepared 2 videos for this one instead of going for a couple hours class, but I'm sorry. I just wanted to let you know, I didn't want to make a break, because article 3.1, 2, and 3, all these 3 are in a continuation, and that's why I took it together. We are not going to study article 3.4, 5, 6, or rest of the articles from this chapter. Now we are going to start the new chapter, not now, next time, new chapter, that is chapter number 4. Because from this chapter 3 and chapter 4, some selective articles we are going to learn, which are really useful to us for our further study. Thank you so much, guys. And let me save this one too. So save, and now I hope all you guys are getting this thing. So let me clear this screen too. Stop sharing. Okay, and let me stop.